Hi everyone, my next topic is color perception. Here are the learning objectives. We'll talk about the nature of color and also the function of color. We'll see how we can describe and quantify color. We'll also take a look at the words that are used in at least English when it comes to describing color. Then we're also going to compare English to other languages as well. Next, we'll move on to putting colors together. There's additive and subtractive color mixing. Sometimes when we put colors together, there are interesting results. I'll talk about complementary colors and primary colors. With number 5, we'll go into some of the theory that tries to explain our perception of color, trichromatic theory and opponent process theory. And what we're going to see is that there's evidence for each one of these. Even though these are kind of opposite theories. Well, wait a minute, they can't both be correct, can they? Oh, can't they? What will inform our understanding of color a little bit is looking at color deficiencies, and then on into some perceptual constancies. Color constancy, which is a pretty remarkable thing, but it occurs because we have other information at our disposal. I'll talk about what that information is. Then we'll examine lightness constancy, which doesn't have anything to do with color per se, but I'll throw it in there too. Once again, we have other information at our disposal that allows us to maintain this perceptual constancy. And then number 9, actually a fairly long section, but it didn't really go anywhere else. There are some interesting things as a result of color, which I want to go through. But first, we need to think about a little bit about the nature of light, which gives rise to the experience of color. So color is not something that occurs in the physical world. It's something that exists in our heads. What? There's no color in the world around us? Actually, no. There is light, and light has wavelength. That is a physical property. But color doesn't exist in the physical world. It's not something studied by physicists. Do you see how those people dress? I don't think they have any color vision. I'm kidding. I kid because I love. Color just exists in your head. It is the result of the way that we process different wavelengths of light. If you think about the nature of color too, and this seems like a simple kind of a question, is a red apple red? Well, maybe the answer is, duh, yes, of course it is. But if you think about it for a little bit, so you've got white light shining on an apple, and white light contains all the different wavelengths, all the different colors of the rainbow. But the skin of the apple absorbs a lot of those wavelengths, and it reflects others. We see a red apple as red because it absorbs all of the wavelengths except for red. It's like a selective mirror for just red. Does the apple have any inherent redness in it? No, it kind of doesn't. That's a pretty deep thing, isn't it? What does it matter if we have sensitivity to color? I mean, does it just help you coordinate your wardrobe? Those physicists. No, there are other reasons aside from just coordinating the colors of your tops and your bottoms. Sensitivity to color is important because it aids in perceptual segregation. Now, this is something I've talked about before in terms of figure versus ground segregation, which is one kind of perceptual segregation as well. If you can detect color, this gives you another tool in the toolbox to separate objects from their background, things like predators and prey, for example. Turns out that octopi, I believe that is the plural of octopus, octopi are really good at camouflaging, and I've got a pretty amazing video to show you. I'm not sure if I can embed it in this video. It might be copyright, and YouTube might reject it for that reason. So if there's no video coming up, I'll have a link to it posted in eClass, so check that out. That's right, I'm going to post that in eClass. Come at me now, YouTube. All right, so hopefully you watched that octopus video. That is just bananas. That's crazy that that octopus can actually do that. Now, of course, what that is an example of camouflage, which animals are amazingly good at. And in researching this, it turns out that camouflage isn't one thing. There are different kinds of camouflage. Who knew? So I just want to go through these 4 types of camouflage. One is called crypsis. So this means an animal blends into the surrounding environment, as we saw in the octopus video. But there are other kinds too. There is concealing coloration. Okay, color, that's what this lecture is about. I think I'm on pretty solid ground here. In concealing coloration, the animal, through evolution, has the same color as its environment, like a snowy owl. That's really hard to see that owl in all that snow. Now, the next one was a bit of a surprise to me. Disruptive coloration, like zebras. And for the longest time, I thought, well, zebras are maybe an exception to evolution because they really stand out from the background. But if you get a bunch of zebras all together and they're just eating grass or whatever, and then some predator comes along and they see the predator, what they're going to do is scatter, and they're going to run in a bunch of different directions. And you've got all of these striped zebras going in different directions, and the predator is like, I don't know which one to pick. So it's called motion dazzle. Prepare to be dazzled. Check this out. Which direction are these stripes moving in? Yes, they're moving in all directions. That's pretty dazzling. All right, next we have mimesis. So in this case, an animal is either camouflaged or concealed because it looks like some other object. And this one gets broken down into disguise. So an animal protects itself by looking like another unimportant, maybe non-edible thing to predator or to prey as well. Good example is a walking stick, like in Bug's Life. Come on, that's a cherished Pixar movie, A Bug's Life. Didn't you love that walking stick bug? Didn't you? Really? If you loved him so much, what's his name? I thought you said you loved that movie, but you can't remember his name? Okay, his name was Slim. The other subtype of mimesis is mimicry. Now, in this case, an animal has evolved to look like another animal that is either distasteful, like literally doesn't taste good, or dangerous. An example of this is the scarlet king snake, which has evolved to look like the eastern coral snake, which is venomous. The scarlet king snake is not venomous. But if you're a predator, it's like, well, those are pretty... I'm just going to stay away from all of these kind of snakes. Okay, so that's kind of why we have color perception. It can help us potentially to defeat camouflage, but then camouflage can get trickier. It's like an arms race that really never ends. Okay, so what we want to do now maybe is to describe color and to be as accurate as possible. We need to go back a few years and turn to Sir Isaac Newton, who of course very famously loved playing with prisms, and he would split sunlight into its component colors. Now this came as quite a shock to people because he took white light, sunlight, believed to be absolutely pure, and by passing it through a prism, split it up into all the garish, brightly colored colors of the rainbow. Now the wavelengths correspond to most colors. We'll get to that in a second. Here is the spectrum, so the colors in the rainbow. And we can remember those by remembering Mr. Roy G. Biv. Roy G. Biv, who lives in the rainbow and tells us the color names in order: red, orange, yellow, green, blue, indigo, violet. Remember that we are starting at the longer wavelengths with the red and moving to the shorter wavelengths, the violet. 7. You know, I have always wondered about indigo. Does it really seem like it belongs with the others? Yeah, I don't think so. So Isaac Newton wanted to have 7 colors in the rainbow. That seemed to him like the right number because he wanted it to match the number of notes in a musical octave. Wouldn't that be like a very beautiful parallel if music and color both had these 7 basic units to work with, so he had to come up with indigo. I don't really think you belong, indigo. Sorry if that hurts your feelings. These are, of course, the spectral colors, and they're called that because they are found in the rainbow. You look at a rainbow and you can see red, orange, yellow, green, blue, violet. But that's not all the colors that we can see. What about purple? We can see purple. And no. Violet and purple are not the same. Purple, if we were to take a look at it and break it down, is actually a combination of red light and blue light. So you get red and blue together, and that makes purple. Yeah, I know it kind of looks like violet here. Look at, this is what I got off the internet. Don't blame me for this. So if purple is red at the long end and blue kind of towards the shorter wavelength end, what if we took this one-dimensional strip and like closed it in on itself, turned it into a circle, and that's what Newton himself did. So we have going around the circle, red, orange, yellow, green, blue, violet. And here we have other colors like magenta, which is closer to red, and purple or red-violet, or RV. Okay, this is wonderful. So Newton has taken this one dimension of wavelength, which was missing a few colors, and then kind of wrapped it around to itself. And now in the color circle, we have all the colors that we can see. Well, most of them. Cartoon time. This is the cartoon color circle. Can you find your favorite cartoon character? This won't be on the exam, by the way. Unless you want it to be, let me know. So color, we gotta unpack that word because it's actually very rich. It's not one single thing, mathematically or kind of physically speaking. Physically meaning in terms of physics. There are actually 3 dimensions to color. First off, as I've talked about, there is wavelength, which corresponds to hue. Okay, so the first word I'm going to give you is a physical, that is a physics word, and then the word after the slash is a psychological dimension. Wavelength corresponds to hue. And no, it's not like they are 2 words for the same thing. There is a subtle but important difference. Wavelength describes the physical property of light. Hue describes our experience of that. Again, subtle distinction, super important. But there's more to color than just wavelength / hue. There's also purity / saturation. So in this case, I have taken one particular wavelength, so a long wavelength. Okay, yes, it's red, okay. Over at the right end, this is very pure or very highly saturated. On the left end, well, it's not red at all. In fact, this is a gray square. It is impure or unsaturated. What that means is that as I've gone from right to left, I've actually added more wavelengths into it. And by the time I get to this gray one, there is an equal balance of every different wavelength. So it doesn't have a particular color to it. It is achromatic. It is colorless, ranging from black to white. And the last one we have is intensity or brightness. Now you can see there is a bit of hue to it, a bit of pinkish reddish, which you can see at the rightmost boxes. You can't see the very rightmost box because it's white. It's as white as I can get it and actually blends into the background. Over here on the left, it's black. There is no light present. At least that's the best I could do. So these are 3 independent dimensions: wavelength and hue, purity and saturation, and intensity and brightness. Each one of those can be manipulated independently. Now, there are some qualifications here. Only spectral colors can be hues, okay? Only the colors of the rainbow. So you're not going to find a hue of brown, no, or purple. Again, purple is not in the rainbow. Remember, it's a mixture of red and blue. So we have to take individual ones and then put them together. Starting to get a bit more complex. So we've got these 3 different dimensions. How can we represent 3 dimensions at once? Well, it's a little bit tricky, and one way of doing it is through what's called a color spindle. Spindle simply describes a 3-dimensional shape, kind of like a spinning top. It actually has all 3 dimensions. So if we were to take a horizontal slice through the color spindle, we would get a circle. The color circle. So as you go around the color circle, you have different hues or wavelengths. If you are right in the very middle, that's essentially like mixing together all of the hues together. And it is a very unsaturated color right in the middle. But as you go out towards the edge of the disc, you are increasing the purity and saturation. So right along the rim of the circle at the outer edge, we have highly saturated colors. Now imagine we have a bunch of color circles and we stack them on top of each other. Each color circle differs from the others in terms of the overall amount of light that's present. That would be the brightness. It is possible to get a pure wavelength, say a nice green, but if you increase the intensity to such an amount, you will experience it as white. And if you're experiencing it as white, you're about to burn out your retina. But for a brief moment, it will appear to you as white light. So that's why it kind of comes to a point. You can take any hue and increase the physical amount of light until it appears to us to be white. That's a bit counterintuitive, but let's think of the opposite as we decrease the brightness. So it's like you're turning down the light. You might have a brilliant red apple in front of you, but if there's no light present, it's going to look black, because everything looks black, because it's dark. So the idea behind the color spindle, it is a 3-dimensional solid that represents and describes all the colors we can see now. Again, one slice taken through it is a color circle, and, well, this is not quite the true story. And that's because some hues saturate before others. Let me get to that in just a second, but let me show a color spindle in color. Okay, so it's been kind of cut in half and like split apart, so you can kind of see the color circle inside. Again, as you go around, you have different hues. You've got red, orange, yellow, green, blue, violet. And as you go towards the middle, it's kind of grayish right in the middle because we're adding together all of these hues. And then we've got brightness. At the tip top, that's white. And at the very bottom, we have black. Now, the color spindle is kind of a hypothetical thing. This is not hypothetical. It's called the Munsell color tree, and it dates back to 1915. So people who work with color wanted to have a way to represent and see as many colors as they could. So this tree has a number of leaves, okay? So each one of these things is kind of a leaf, and as you go up, they are brighter, essentially. As you go down, they get darker into black. Each leaf represents a different hue, and as you go from the center out to the edge, you're getting a more pure color. The Munsell color tree. And here's a couple of leaves from the tree. And I wanted to show these to you because this gets to that statement that I just let hang, that some hues saturate before others. So yellow is a really good example because yellow saturates and you can't saturate it anymore. You can't see as many different shades of yellow as you can of other different hues. So here's some violets. Violet has a lot of depth to it. You can see a lot of different violets. The same is true of green. You can see a lot of different greens. Not all colors are created equally. So that nice round shape of the color spindle, that's a bit idealized. In reality, no, not all hues are created equal. All right, let's continue to describe color. I know one of the questions that people like to ask is, how many colors are there? That's a good question. So it's almost impossible to identify colors. The next best thing is to discriminate, that is, tell the difference between colors. This is tough to do. So in 1939, it was estimated that we can discriminate about 10 million. How did they do that? On the back of a napkin or something? I don't know. So it's kind of just a guess. That's quite a nice round number. It seems improbable. In 1991, a more scientific approach was attempted in which each of the three dimensions of hue, saturation, and brightness was examined separately. Like, how many different hues can we see? About 200. How many different steps of saturation can we discriminate? Approximately 20. How many different levels of brightness? About 500. You multiply 200 times 20 times 500, and you get 2 million different colors. Again, this is an estimate. We can't really count them up, but it's fairly widely accepted these days. Now, if you are watching this, you're watching it on some kind of a device with a screen which can display something like 16 million different colors. You might have a display that can produce even more than that. So, whoa, you must be rich. But you know what? I think you're overspending because, again, we can only discriminate something like 2 million different colors. Now, discrimination is different from identification. Identification means putting a name to something. When it comes to color names, well, that study from 1939 also kind of went through a dictionary and they counted up words that could be applied to colors in English. And there are about 7,500. These aren't color names like if you go shopping for makeup and you get lipstick, that's like Sierra Sunset and Sierra Sunrise, and they're totally different, but they're still shades of pink. Okay, it doesn't include those kind of made-up names. If we compare English to other languages, though, other languages are not the same as English necessarily. So, for example, the Dani people of New Guinea have two color terms: Mili, which is cool dark colors, and Mola, warm light colors. Do these people have some kind of genetic defect in which they can't see colors? No, they can see colors just like we can, but their language only has two color terms, interestingly. How about Swahili? Nyekundu refers to brown, yellow, or red, so quite a chunk of the spectrum. In Welsh, there's this word, which I'm not going to try to pronounce, which covers blue, gray, and green, and Japanese has a word which covers green and blue. Yeah, again, this doesn't cover made-up names. I think it's interesting sometimes to see the kind of made-up names. So here's some recently from Sherwin-Williams, who felt that they were not capturing the entire market of people who are shopping for paint. It seems that the names that they had come up with previously more appealed to women. So what they did was coin new names that would more appeal to men. So I want to show you the old names and then the new names. So that color right there, it's called Peacock Plume. And I guess that didn't appeal to the bros, so they renamed it Pimpin' the Trans Am. Okay, bros, does that appeal to you? Lexington Park versus Dudes Like Dirty Socks. Am I right? Am I right, dude? Romance. Bromance. Juliet's Potion. Zombie Apocalypse. Plum Escape. Sucker Punch. Classic Liberty Red. Rust on my truck. So you can see they're trying to appeal to men. I don't have any data on if this was more effective in selling paint to dudes. So coming back to languages and color names, one of the longest ongoing studies in science is called the World Color Survey, and you can see periodically they do publish their results. It is not a psychological or perceptual study, but an anthropological study of the color terms in now 110 different languages. They found an interesting common pattern. Some languages only have two color terms. And if they have these two color terms, it's not like, purple and burgundy. No, it's light and dark, kind of the mola and mealy. Some languages have three color terms, and if that's the case, again, there's this universal pattern. It's basically equivalent to light, which means white, warm, which is red, yellow, and brown, and dark, which includes black, green, and blue, or GRU. Seriously, this is what they call it in anthropology, GRU. GRU refers to the part of the spectrum from green to blue, but it's not differentiated. You don't pull out and differentiate green and blue. Again, some languages have more than three color terms, and again, there's this universal pattern that happens over and over and over. The warm part is always split into red and yellow before GRU gets split into the specific names for green and blue. Again, it's a regular pattern that happens every time. It's been found that the so-called basic hues of black, white, red, yellow, green, and blue are named before any other color terms. Some languages are very rich with color terms, and if there are 7 or more, the words for brown, orange, pink, purple, and gray are added before green gets subdivided or blue gets subdivided. So, for example, chartreuse is kind of a yellowish green, named after this liqueur, and azure is one more specific shade of blue. So again, the point of this is that there is an invariant sequence of emergence across languages. Starting off with basically black and white, red typically gets named, then green or yellow, blue, followed by brown, and then orange, pink, purple, and gray. So I did a little bit of research on my own, going into Google, actually, yes, Google, and they have a tool called the Ngram Viewer, which counts up the number of mentions of a particular word in time, starting back in 1800. So I put in a bunch of basic color terms. So white and black, very, very popular. So really more popular than any other color terms, followed by, interestingly, red, clear, number 3, and then blue and green pretty close together, and then yellow, brown, orange, pink, and purple. So it's kind of like the Berlin K order. But why? This describes this phenomenon, doesn't explain it. Now, this study is not intended to go into the why exactly, but they do speculate a little bit, and they suggest it's due to commonalities in the physiology of the visual system, which we'll be getting to coming up in a little bit. Now, this might represent why some colors are more popular than other colors, potentially. In the Western world, blue is a very popular color. In a lot of Asian countries, red is a very popular color. I did a bit more research and I found this, which shows the logos of some of your favorite companies and where they would fit on the color wheel. Yeah, it's pretty crowded. That's not necessarily representative. There's actually a lot of companies that have a blue logo and a lot fewer that have a purple logo. Okay, so we can see that even describing an individual color is a little bit tricky. But what if we want to put colors together? Remember, red and blue is purple? So now I want to turn to color mixture. With a bit of an experiment that I wish I could do in person, if we have light that has a single component wavelength at 570 nanometers, that is a yellow. It's a very lemony, canary yellow color. But then, if we have two other beams of light, one that's green and one that's red, and you overlap them and shine that into a person's eye, they will see that as yellow. In fact, it's going to be identical to the first yellow. They are indistinguishable. Their underlying physical components are different, but they are seen as being identical. This is the case of what are called metamers. We've got two different distributions of light, different wavelengths, but they are identical in color, and there's nothing you can do. You can look at it and squint and think as hard as you can, but you cannot distinguish these two yellows. They are identical. So what we must conclude from this is that metamers result in identical neural activation. There's no difference. Now, when it comes to mixing colors together, there's two ways of doing it. One way is additive color mixture, and I'll talk about this in terms of the metaphor of putting together light of different wavelengths. So, as I just talked about, if we mix together red plus green, that produces yellow. If we mix all the colors together, that produces white light. So it's kind of the opposite of what Newton did with the prism. If we take all the colors of the rainbow together and overlap them and shine them, it produces white light. So for example, you're looking at additive color mixture right now on your computer screen. Yeah, so typically your screen is made up of red, green, and blue pixels, sometimes called RGB. So I've zoomed in really lots here in this one, you can see. And if you stick your face way too close, if I put my face right up close to this guy, I still can't see it. No, they're too small. Need a magnifying glass or something. So your screen is only showing you red, green, and blue of differing intensities, but if you're far enough away, they will blend together and create 16 million different possible colors. The other way of putting color together is called subtractive color mixture. We're taking away colors. This one is actually a bit trickier to understand. The metaphor is that you're mixing paint or maybe ink together, each paint having different pigments. So if you've ever done finger painting, I have fond memories of doing finger painting as a kid. They don't really do that anymore, probably because it's too messy or the kids would eat the paint, I don't know. But if you mix red and green paint together, you get kind of a disappointing grayish brown, not a lot of fun. If you keep mixing other paints together, eventually you're going to get really dark gray or basically black. It's kind of the opposite of additive color mixture. You might have some experience with this. If you have an inkjet printer, they will mix pigments together. Although you can get fancier printers that have 4 different pigments. Ooh, you must be rich. The one that I have mixes yellow, magenta, and cyan ink tanks together. And mixing those together can produce virtually any color you'd like to have. But how does this exactly work? So it's called subtractive color mixture because what paint does is it subtracts certain wavelengths. This comes back to the whole, is a red apple red thing? It wasn't just a philosophical question, it's important. So if there's something that looks blue to you, that's because it's absorbing a lot of the red, a lot of the orange, a lot of the yellow. It's going to be reflecting, of course, a lot of the blue, but also a bit of the green. It's tough to get paint that reflects a single wavelength. It would be tremendously rare and very expensive. Let's take a look at yellow paint. Again, the same kind of a thing. It absorbs all the red, all the orange, reflects a lot of the yellow, but also reflects some of the green. Interestingly, so both blue paint and yellow paint reflect some of the green. So let's mix together a blob of blue paint and a blob of yellow paint, and what we get then is, of course, well, green. So what's happening? The blob of paint is absorbing all of the blue, and that's because of the yellow paint. And it's absorbing a lot of the yellow and the orange and the red. That's because of the blue paint component. Now, the one thing that the blue and the yellow paint have in common is that they both reflect some green. So when you mix blue and yellow paint together, it subtracts all of these wavelengths except for the green. I know it's a bit tricky. You have to think in terms of negatives to understand subtractive color mixture. Here's another visual example. This might help a little bit more. I've got a blob of blue paint. I've got a blob of yellow paint. So blue paint looks blue because it reflects a lot of the blue end of the spectrum. It absorbs a lot of the yellow, orange, and red. Yellow blob of paint, kind of different. It reflects a lot of the yellow, absorbs a fair amount of the red, and a lot of the blue. Now, if we mix together a blob of blue paint and a blob of yellow paint, their area of overlap is this region here, which corresponds to 520, 530 nanometers, which we see as green. So this would be an example of subtractive color mixture. Again, it's tough because you do have to think in terms of negatives. Now, there are certain colors that we can mix together and they will produce certain interesting results. One example is complementary colors. Now, it's not just any two colors. We have to go back to the color circle and pick colors that are on opposite sides of the color circle. They have to be exactly opposite from each other. And then, if we take those two colors and add them together, they kind of cancel out. It's not that you can't see anything. There is still some light present, but all the color is gone. It's achromatic. It's kind of a grayish white color. And it doesn't matter what pairs of colors you mix. You can mix together green and red-purple, produces grayish white. Or blue and orange-yellow, it produces the same grayish white. Here's an example of the very first color photograph ever taken. It was not a single photograph. It actually had to be taken 3 times using 3 different colored filters. The film then had to be developed and then projected once again through 3 different colored filters onto the same area of a screen. So it wasn't actually a photograph that you could hold in your hand. It was rather a photograph that had to be projected onto a wall with 3 projectors. And that's how people saw the very first color photograph ever taken. In case you're wondering, it's a tartan ribbon from Scotland. Now, the fact that there are 3 colors that can mix together to create any color is pretty important. These, of course, are the 3 primaries. Now, this is something that the structuralists were looking for. They were looking for the basic elements. The primaries are the basic elements of our color experience. There are 3 specific wavelengths that, when we mix them together in the right proportions, can match any other hue. Now, there's only one catch, there's one limitation, and that is you can pick any 2 colors you want for the first 2 primaries, but for that third one, it cannot be a mixture of the other 2. So it requires what are called monochromatic lights. You cannot use metamers. Again, that would not work. If you had red and green and yellow, oops, no, that wouldn't work, because red and green mixed together produce yellow. Okay, you can't have those 3 as your primaries. And again, primaries were believed to be the basic fundamental units of color sensation. 3 primaries. So once again, we have this issue of how do we put 3 things together in a way that makes sense? We've got 3 dimensions. Well, James Clerk Maxwell created something called the color triangle in 1860. What do you do if you got 3 things? You make a triangle. In this triangle, at each apex, we have one of the 3 primaries: green, red, and blue. And if you want to get a particular color, you get a certain proportion of green, a certain proportion of blue, and a certain proportion of red. The only problem is you can't match all hues inside of this triangle. Like, look for yellow. Yeah, I know you're looking over here. Y for yellow, right? And that's actually the y-axis. There's a y, a z, and an x. And although this is kind of yellow, this is not the spectral yellow. No, it actually doesn't exist. It's actually outside of the triangle. It's like out here somewhere. That's where yellow would be. The problem with this yellow is it still contains too much blue. So even though we're as far away as we can get from blue, we still have to subtract more blue, which means moving far out of the triangle. Okay, that's kind of awkward and difficult to deal with. It's not very elegant of a solution. So people kind of thrashed around for a few decades until finally, in a meeting of the Commission Internationale de l'Éclairage, they hashed out a way of incorporating all of the hues that we can see. Now, the triangle didn't work, so they used kind of a bigger so-called imaginary triangle. This is called the gamut. If you've ever heard the word "you run the gamut," gamut is actually a technical term that represents all of the colors. So I think the reason it's called an imaginary triangle is it's not really shaped like an actual triangle. Not exactly. Again, as you go around the perimeter, you can see we're going from red, orange, yellow, green, blue, and violet. And here in the middle, where they all come together, you can see they start to cancel out, and it's achromatic. Now, this is still a two-dimensional figure, so along the x-axis, we actually have the amount of red, and then along the y-axis, we have the amount of green. And if you look really closely, the green goes up to 0.8, and that's kind of where the gamut ends. It doesn't even go up to 0.9. And the same thing with the x. This is the reddest red possible, and it's just barely above 0.7. So at least it's possible to get the amount of green and the amount of red in any color. But how do you get blue? Okay, so what you have to do to get blue is actually do a little bit of math. No, not math. Yes, just a little bit of math. So again, you get the proportion of green, the proportion of red from the graph, and then you subtract that from 1.0, and mathematically, you get the proportion of blue. See? It's not that hard. Now, this gamut represents one slice of intensity. If you imagine these all kind of stacked up, that would then account for brightness. So each slice has a different level of brightness. So what you can do now is specify any hue in terms of these primary colors. Problem solved. And I do want to point out an application of the CIE chromaticity space if you're buying a television, for example. Especially a high-definition television. They're based on the Rec. 709 color standard. There we go. If you have an ultra-high-definition TV, including a 4K TV, that's based on the Rec. 2020 standard. And if you take a look at the gamut, it's actually larger. If you take a look at the triangle inside of the gamut, it is way bigger. Now, when you're shopping for a television, if you want to have the richest color experience, you'd want to get one that has a triangle that is as close to the human eye gamut as possible. So you can see the 2020 is a much larger triangle than the 709. Now, I did say something about displays having 16 million different colors. Within this triangle, a typical computer or a TV display can subdivide all of the colors within this triangle into 16 million. So very, very fine divisions. That's good, but again, what we're really looking for is a display technology that can actually match the gamut. So if you do go shopping for a TV, here's an example from a particular website. Some of these websites actually do show you the color gamut of the TV that you would like to buy. So you can know that in advance. And I'll stop there.